All right, so in this lab, we're going to be taking a look at melting point of two different substances. First, we got cane sugar, and we'll take a look at what a molecule of that looks like. And we have sodium chloride. We got table salt over here. And this is an ionic compound, so we'll take a look at the differences between a covalent molecule and an ionic compound. And we got a little pan over here. We're going to be heating up just on a gas stove and seeing if they can melt on a stove. So I want us to take a little bit of a look at what each of these look like. First, we're going to look at one molecule of sugar. This is also called sucrose. And I want you to look at what type of intermolecular forces might be here. So take a look. And what I want you to notice is it's a large molecule, but I want you to notice all throughout here we have several locations where sucrose can hydrogen bond with other sucrose molecules around it. I think I got all of them. Yep, so we got 1, 2, 3, 4, 5, 6, 7, 8. 8 locations with partial charges that will attract those sucrose molecules together. So the other thing we're looking at is table salt. So we've talked about table salt. It is an ionic compound. So it bonds differently than this. In each of these bonds, in this molecule, they're sharing electrons. In our ionic compound, you remember our sodium gave up an electron and the chlorine took it and became a negative chloride ion. And then with negative charges, they attracted together. So we're going to be looking at which one of these will melt easier. So if this was what a solid was, a liquid, these would break apart and they'd start moving past each other. So that's what it would take to make our ionic compound into a liquid. If our sucrose became a liquid, it would stay a whole sucrose molecule like this. It would just lose its intermolecular forces with the other sucrose around it, and they'd be moving around as whole molecules still. All right, first up, we're going to be doing sugar. And to keep it as scientific as possible, we're going to be trying to use about 50 milliliters of each, seeing how long it takes to heat it up. And I'll just put it on high, so it'll be the same for each. So we'll throw it on, start my timer over here. Let's see. All right, got my timer started. Oh, stove isn't wanting to work. Have to restart that timer. All right, there we go. Timer started. So we don't want it to burn. That is exactly what we don't want to do. So I'm gonna keep mixing and we'll just see what happens. All right, we're coming up to 2 minutes. I'm not noticing much of a difference here with sugar. Oh, wait a second. Uh-oh. We got a little bit of melting going on. You could see the melting. Happened right around the 2-minute mark. And you could see how that sugar is starting to become much more of a liquid. So it's been 2.5 minutes now. We'll wait till we get it all liquidy. Alright, so that took roughly 2 minutes and 50 seconds at full heat. So that's about how long it took to melt that sugar. And it looks like it's caramelized pretty well. So if you want to try this at home, make sure to ask your parents first. But you can make a little bit of caramel. Alright, this time we got salt, table salt, sodium chloride. Looks basically the same. It's a white crystal. We're starting our stopwatch over. We're going to put it on high heat. And we got our timer started. So we'll see what this looks like. I'll be continuously stirring it. Alright, we're coming up to 2 minutes. Not seeing much, if any, melting going on. You may be seeing a little bit of a color change there. Looks to me like it's getting a little bit browner. Can you blow that out for me? Can you open the window? Alright, so it's been 4 minutes. You may see some of these black dots. That would be the anti-caking in the salt. We have a little bit of dextrose, which would be burning at about this temperature. But the salt itself is not melting. So we'll go for 1 more minute, see what we get. Alright, so it's been 5 minutes. I'll turn off the heat, kind of give you a closer look at what's going on. You might see some steam coming up. That would be the dextrose in the salt. That's what kind of helps it from clumping up if it gets a little bit moist. But the salt itself, it's still completely solid. So I would not recommend to try this one at home. Alright, so I want to come back to this a couple weeks ago. And all of these intermolecular forces, dispersion, dipole-dipole, hydrogen bonding, they all are in our covalent molecules. Dispersion was with anything with an electron, molecules and atoms, and it was that partial temporary charge caused by a shift of electrons, so it's temporary. A dipole-dipole moment is also a partial charge in a polar molecule, and a hydrogen bond was just a stronger type of partial charge. But we have even some things with stronger attractions, and that would be ionic bonding. You could think of it as just when two ions are attracted together. And just like in salt would be like our example, these aren't partial charges anymore. These are whole charges. So because they're full charges, sometimes you even have multiple charges there. So like magnesium would be a 2+, or oxygen might be a 2-. These whole number charges have a stronger attraction to themselves than our other intermolecular forces with partial charges. So these ones are between ions, and they are very strong. Especially when you compare them to our intermolecular forces with covalent molecules. So an example. So because with our covalent molecules, our intermolecular forces are significantly weaker than our whole charges in our ionic bonding, that influences the melting point of a lot of our compounds that we see. So we're going to see a trend here. So let me share with you guys this right here, and we'll zoom in. We talked about these three types of bonds: covalent bonds, metallic bonds, ionic bonds. They form different types of compounds. In general, covalent molecules, water, oxygen, nitrogen, the air, carbon dioxide, sugar. In general, our covalent molecules have the lowest melting points. I'm just going to put low there. A lot of them are even gases or liquids at room temperature, so they're already melted at room temperature. And then our ionic compounds with those opposite charges, those opposite whole charges, have very, very high melting points. And then metals would be in the middle. If we were in the lab, we'd be melting a few metals, and you would see how some metals melt at much lower temperatures than salt. So again, this is kind of a rule of thumb, but in general, covalents are lowest, metallic compounds will be in the middle, and ionic will be our highest. But there are a lot of factors that go in there. All right, so after watching sucrose melt on the stove and the attempt of melting salt on the stove, I want to show you guys what the actual melting points are. So for sucrose, it melts at about 186 degrees Celsius, which is pretty high. But when we compare it to sodium chloride, which melts at 801 degrees Celsius, it's very, very low. So again, back to this, our covalent compounds usually have much lower melting points than our ionic compounds. And that's because of the full charges in between each of those ions. So I want to take this opportunity to show you guys some other melting points of some ionic compounds. And you can see in general, I got sodium chloride on top with plus and minus 801 degrees Celsius. And on the bottom, we got magnesium oxide plus 2 minus 2. So you have twice the charge, and you can see the melting point is much higher. So in general, the larger your charge, the more they'll be attracted to each other. So you'll have a higher melting point the more charges. And that's a very general statement because it's not always the case. You could see here, magnesium has a 2+, chloride has a -1, and its melting point's actually lower than sodium chloride, which just has a +1. So there's a lot of other things that go into melting point. Other things that are really big would be the size of these ions and what structure they can form together.